There is a moment 13.8 billion years ago that cosmologists call the beginning of everything. But here's the part that keeps physicists up at night. That moment might not actually be over. Somewhere, right now, in some patch of reality you and I will never see, the Big Bang could still be happening, not as history, as an ongoing event. Today we are going to ask what happens if the Big Bang never ended, and why some of the most respected minds in physics think that is not science fiction. It is the default outcome of the math. Stick with me, because by the end of this you will never look at empty space the same way again. Let's start with what actually happened, or what we think happened. In the earliest fraction of a second, the universe underwent something called cosmic inflation. This idea comes from physicist Alan Guth, who proposed it back in 1980 to solve a handful of problems standard Big Bang theory could not explain. Inflation says that space itself expanded faster than the speed of light for a fraction of a second, stretching a region smaller than an atom into something the size of a grapefruit almost instantly. Yeah, faster than light. Space itself gets a pass on that rule. Only matter and information are stuck obeying speed limits. Once inflation ended, that burst of energy release is what we call the Big Bang, the hot, dense soup of particles that eventually cooled into stars, galaxies, and eventually you. Reading this sentence in your head, here's the twist. Guth and later physicists, including Andrei Linde and Alexander Vilenkin, realized something strange about the mathematics of inflation. Once it starts, it is incredibly hard to stop everywhere at once. Inflation is driven by a field of energy that behaves almost like a ball balanced on a hill. In our patch of the universe, that ball rolled down into a valley, ending inflation and triggering our Big Bang. But quantum mechanics says that in other regions, the ball can randomly stay stuck higher up, still inflating, still expanding at that impossible pace. This is called eternal inflation, and it means our Big Bang was never a single event. It was one bubble popping in a bath that never stops bubbling. Now here's your call to action, because this is exactly the kind of question worth sitting with. If this idea of an unending Big Bang is blowing your mind a little, hit subscribe, because every week on this channel, we take one real scientific framework and push it as far as the evidence allows. No fluff, no fake science, just the actual physics taken to its logical extreme. Drop a comment telling me which universe you would want to wake up in, because trust me, some of the options coming up are not friendly. Alright, let's keep going, because this is where things get genuinely strange. So what would it actually look like if the Big Bang never ended? Picture the universe not as a single expanding balloon, but as an infinite frothy ocean, where every so often a bubble of low-energy nucleates inside the high-energy sea, and that bubble becomes a universe of its own, with its own Big Bang, its own laws of physics, its own possible history. Our observable universe, everything the Hubble and James Webb telescopes have ever photographed, is just the inside of one bubble. Outside that bubble, inflation is still roaring on, stretching space so fast that new bubbles can never catch up to each other, never collide, never even know the other exists. Vilenkin calculated that once eternal inflation starts, it never fully stops. Mathematically speaking, it is eternal into the future by definition, which is honestly a wild thing for an equation to casually tell you over breakfast. Let's ground this a little, because I know that sounds like pure speculation. The evidence for inflation itself is not speculation. The cosmic microwave background, the faint afterglow of the early universe mapped in incredible detail by the Planck satellite, shows a uniform temperature across the sky to within 1 part in 100,000. That uniformity is very hard to explain unless some process like inflation smoothed everything out before the Big Bang proper began. So the foundation, inflation happened, is on solid observational ground. It's the eternal part, the part where inflation never globally ends, that remains theoretical, but it falls directly out of the same equations that already passed the observational test. That is why so many cosmologists take it seriously instead of laughing it off. Now let's escalate, because if inflation truly never ends, the implications get uncomfortable fast. If new bubble universes are constantly forming in the eternally inflating sea, then there could be an infinite number of them, each with different physical constants. Some might have a stronger nuclear force, collapsing into black holes before atoms even form. Some might have weaker gravity, spreading out into cold, starless nothing. Somewhere in that infinite foam, by pure statistics, there would be bubbles nearly identical to ours, with a planet like Earth, with someone who looks exactly like you. Reading a slightly different version of this sentence. That is not a metaphor. That is a direct mathematical consequence of infinite trials in an infinite multiverse. And it is one of the reasons the multiverse idea makes some physicists deeply uneasy, because it borders on unfalsifiable. If literally everything happens somewhere, what does the theory actually predict? Here comes the dark turn, because eternal inflation is not just infinitely generous, it is also infinitely dangerous. Those bubble universes are separated by walls of extremely high energy, and every so often, two of them can theoretically collide. If our bubble ever collided with another one, the collision would not look like an explosion in the sky. It would look like a wall of altered physics sweeping across the universe at close to the speed of light, rewriting the rules of reality as it passed. Anything caught in that wave would not die in the normal sense. Atoms would simply stop behaving like atoms. Some cosmologists have actually searched for faint circular imprints in the cosmic microwave background that might be the leftover bruises from an ancient near miss with another bubble. So far, nothing conclusive has turned up. But the fact that scientists are seriously scanning the sky for scars from other universes tells you how far this idea has traveled from fringe theory into mainstream cosmology. There is an even darker cousin of this idea called false vacuum decay. Some physicists, including work associated with theorist Sean Carroll and others studying the Higgs field, have pointed out that our own universe might currently be sitting in a false vacuum, a low but not lowest possible energy state, like a ball resting in a shallow dip on a hillside instead of the true bottom of the valley. If a bubble of true vacuum ever nucleates anywhere in the universe, through sheer quantum chance, it would expand at the speed of light in every direction, and there would be no warning. One instant, everything is normal. The next instant, because nothing can outrun the wave, the fundamental constants of physics change, and nothing that exists could survive the transition. It is simultaneously one of the least likely and most absolute ways the universe could end, and calculations suggest we are probably stable for a very long time, but probably is doing a lot of heavy lifting in that sentence. Let's push one more rung up the ladder before we hit the climax, because there is a version of this that gets even stranger once you factor in time itself. In an eternally inflating multiverse, time may not even be a single shared clock the way it feels to us. Each bubble universe essentially runs its own private stopwatch from the moment it nucleates, which means asking what time it is right now across the whole multiverse is a bit like asking what time it is on the surface of the sun using your kitchen clock. The question does not translate cleanly across the boundary. Some cosmologists studying what is called the measure problem have pointed out that if you try to count events across infinite bubbles to figure out which outcomes are more likely, you run into paradoxes where almost any answer can be justified depending on how you slice the infinity. That sounds like a technicality, but it is actually one of the biggest open problems in modern cosmology, because it means our best model of the very large-scale structure of reality currently cannot even promise us consistent odds. Physicists like Andre Linde and Alan Guth have both written about this measure problem candidly, treating it less like a footnote and more like a warning label stapled to the whole framework: useful, powerful, and still missing a piece. And here's where the picture gets almost unbearably vast. If our observable universe is roughly 93 billion light-years across from edge to edge as we currently measure it, that number, staggering as it already is, might be an almost embarrassingly small crumb compared to the true size of the eternally inflating background stretching beyond it. We are not just small compared to the galaxy, or small compared to the observable universe. We may be small compared to a foam of reality so large that light itself, the fastest thing that exists, could never cross a meaningful fraction of it, even if you gave it the entire lifespan of our universe as a head start. Try sitting with that for a second, because most people go their entire lives without ever confronting a number that big, let alone a number that describes the literal size of the stage they are standing on. Now let's reach the actual climax of what an eternal Big Bang means for the long-term future. If inflation truly never globally ends, then the eternally inflating space is not just the birthplace of bubble universes. It is also functionally immortal. Long after our own bubble universe cools, stars burn out, and black holes evaporate through Hawking radiation over spans of time so vast that current numbers barely have names for them, the inflating background outside our bubble keeps producing new universes, new Big Bangs, new chances for physics to roll different dice. Picture it as a fireworks show that never actually finishes, where every burst you can see is just one shell in an endless sky, most of which will never be visible from where you are standing. Some physicists, thinking about this eternal expanse, have even speculated about Boltzmann brains, the deeply unsettling idea that given infinite time, random quantum fluctuations in an eternal empty universe could statistically assemble a fully formed conscious brain out of chaos far more often than they could ever assemble entire ordered galaxies through the slow process of stellar and biological evolution. It is a genuinely strange prediction that many cosmologists treat as a warning sign that our models of eternal inflation still have something important missing, rather than a literal forecast. So let's pull back from the multiverse foam and the false vacuums and the ghost brains in the dark and ask the human question underneath all of this. If the Big Bang never truly ended, then the universe we call home is not a single finished story. It is one paragraph in a book with no discoverable beginning and possibly no end. Everything you have ever known, every star, every galaxy, every person who has ever lived, exists inside one bubble in an ocean that keeps producing more bubbles forever. That should either feel completely terrifying or strangely comforting, depending on the day. It means the universe was never really about us specifically, and also that the raw creative engine behind existence never runs out of material. We spend so much energy asking how it all started and how it all ends, but eternal inflation quietly suggests those might be the wrong questions, because start and end may only apply locally, to us, inside our one bubble, while the bigger process just keeps going, indifferent, endless, generating new physics in the dark forever. What would you actually want to find if you could step outside our bubble and look back at it from the inflating sea? That is a question no telescope can answer yet. But the next time you look up at a clear night sky, remember you are not looking at the whole show, you are looking at one frame from one reel, in a projector that never stops running. And if bubble universes colliding sounds unsettling, wait until you hear what happens if two of them are moving toward each other right now. That's a story for another What If.